Okay, I think we are live. Welcome everyone. Thank you for joining us for today's Low Physics webinar. My name is Alejandro and I'm going to be your host. Today, we are presenting numerical models of astrophysical black hole accretion flows by Professor James Stone. Jim obtained his bachelor and master's from Queen's University in Kingston, Canada, and then his PhD from the University of Illinois. Then he was a professor at Maryland. Then he went to Cambridge for a little bit, then moved to Princeton, and currently he is at the Institute for Advanced Studies here also at Princeton, New Jersey. His research interests are in fluid dynamics, particularly magnetohydrodynmics, for which he has developed some of the most powerful and used codes in astrophysics. Remember, you can ask questions over email through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. Now, without further ado, we will turn it over to Professor Stone. Thank you for joining us. And thank you, James, for accepting our invitation.
Thank you, Alejandro. It's a pleasure to be here. Maybe I should share my screen.
Yes.
Okay, hopefully you can see that now.
Perfect, thank you.
Great. So it's a pleasure to be here. Welcome, everybody. I thought I would tell you a little bit about some research we've been doing, actually mostly pre-pandemic. This is mostly results that we've obtained in the last 5 years or so on trying to understand accretion onto compact objects like black holes. I apologize if some of you may have seen some of these results at various presentations because they are over the last few years being published. And so there's been some presentations made by many of my collaborators here, which I'd like to acknowledge: Omer Blaze, Shane Davis, Kyle Felker, Yanfei Zhang now at the CCA, Kengo Tomita, Chris White. So it's an effort that's involved many people and over many years to get to the point where we are beginning to calculate these models with full physics that we think is important. So I wanted to just introduce these results and tell you what why this important problems. Well, let me in fact begin by my slides are not. I think I might be sharing the wrong screen. My slides are not advancing here, so let me try sharing that screen.
Yes, perfect. We see now the outline.
Good. So I thought I would first motivate, why this is an interesting problem to study, tell you a little bit about the numerical methods, which are absolutely essential for studying this problem, and then again, talk about some of these results we've had over the last 5 years. So basically, why is everyone so interested in accretion flows? And the answer is very, very simple. Accretion onto compact objects is by far the most energetic process in the universe. It releases far more energy per gram than say nuclear fusion in stars. And so accretion powers all of the most luminous sources that we know in the universe. This includes quasars and active galactic nuclei. And in the stellar context, when we have close binary stars, X-ray binaries, for example, are powered by accretion onto a neutron star or white dwarf in a close binary system. And so we'd really like to understand this gas dynamical process of accretion to understand these very luminous sources. And moreover, more recently, I'm sure many of you know, we've obtained the first image of accretion flows onto black holes through the Event Horizon Telescope. This is a millimeter interferometer with a baseline, essentially the diameter of the Earth. It's obtained very high resolution images of the black hole and in the galaxy M87. It's an elliptical galaxy, supermassive black hole at the center. And we've known about this black hole for a very long time because it produces relativistic jets, which were seen in optical images taken of the galaxy more than 100 years ago, this bright white filament here. And now with VHT, we could actually resolve the center with multiple resolution elements across the event horizon scale for this black hole. And we see this bright ring of emission in the millimeter wavelengths, which is coming from an accretion disk, from an accretion flow on the scales of the event horizon in the system. And we'd like to understand, exactly how this flow is being fed and its dynamics. So while EHT is a wonderful instrument for observing black holes, it's also a fabulous instrument for understanding accretion. It's really a wonderful experiment to understand relativistic plasma physics, because that's what we're actually observing. It's the plasma as it's accreting into the black hole. So these observations really motivate, what we want to do. But accretion comes in many different forms, and the physics you need to include really depends on what mode of accretion you're in. There's a so-called radiation-dominated accretion involving dense collisionless plasmas, where there's a strong radiation field and strong cooling. By strong radiation, I mean the radiation pressure is comparable to the thermal pressure. And typically that involves Eddington ratios, and I'll explain exactly what that is in a minute. The Eddington ratio bigger than, say, 10 to the minus 2, 10 to the minus 3. And the kind of objects that we observe in this state are quasars and X-ray binaries in the so-called soft high state. Also TDEs, or tidal disruption events, are thought to be super Eddington accretion flows. There's also low luminosity accretion disks or accretion flows, where it involves accretion of very diffuse plasma in which the collisional mean free path is typically bigger than the event horizon itself. So the plasma is essentially collision-less. It's very inefficient at producing radiation. It doesn't cool at all. It's essentially adiabatic as it falls in. And this typically occurs when the Eddington ratio is very, very, very small, say 10 to the minus 4 or less. And it turns out that the galactic center and M87, the two sources that the EHT is observing, is in this low luminosity state. And the physics there is very different because it's really collisionless plasma physics. And my focus today will be on the radiation-dominated case, where we need to include the radiation field along with the plasma physics. And that's really aimed towards these high luminosity sources. Despite the interest in these low luminosity sources, I won't say too much more. But I have to say something now. There's sort of an industry in modeling that in them now. There's a large number of groups that are studying EHT-like flows or flows observed by EHT. It involves doing full general relativistic MHD simulations. I'll explain why MHD is so important in a minute. And basically, this movie shows the accretion flow around a black hole as sort of a poloidal slice of the density, showing the time evolution of the plasma as it accretes inwards. And then you can ray trace that or make images, including all the general relativistic ray tracing effects, all of the light bending effects due to the curved space-time of the black hole, to make images of what that would look like at various orientations from 40 degrees to fully face on at 90 degrees. And many of these images are strikingly similar to what the EHT observes. And so we think that we, at zeroth level, understand what the EHT is observing as one of these accretion flows around a black hole. But again, this is in this low luminosity limit where the radiation field is really not very, very important. And I really want to focus on the high luminosity state, where there's sort of many more observations and many more observationally motivated questions of these high luminous accretion systems. So for example, recent X-ray satellite NuSTAR has unambiguously identified ultra-luminous X-ray sources. These are point sources in external galaxies, which have very high X-ray luminosities. They've been unambiguously identified to be neutron stars with a luminosity greatly exceeding the Eddington luminosity, thought to be the highest luminosity you can sustain for an accretion flow. So how does super Eddington accretion occur? It clearly occurs in nature. We now have unambiguous proof that super Eddington accretion occurs. And how is that possible? Moreover, slightly below an Eddington ratio of 1, sub-Eddington accretion disks have a ubiquitous X-ray spectrum that involves not just a thermal spectrum from an accretion disk. So observed is the spectrum of Cygnus X1, a very famous X-ray source accreting a close binary system. And the observed spectrum is this black line, and it can be fit by multiple components, including a thermal accretion disk, but essential is also a corona made up of non-thermal emission from very, very hot plasma. And a very significant fraction of the total luminosity from the source comes from this corona. So how do accretion disks produce these very hot plasma, which produces this coronal emission that we observe? It's a very significant part of sub-Eddington accretion disks. Then finally, one way to measure mass and spin a black hole is by fitting the spectra especially the so-called iron K line profile, assuming a theoretical model, a so-called alpha disk model for the emission from the disk. And can we really compute synthetic spectra from first principles going beyond alpha disks and try to test these continuum fitting models? Because if there is an error in our spectrum, it will mean that the mass and spin that we're inferring from the spectrum is incorrect. We really need to calibrate these spectral fitting models to make sure they're really working. And so this is just a sampling of all kinds of questions that have emerged about luminous accreting sources that theoretical models would hope to try to address. And that's really our goal, is to try to address these questions. And so what are we going to need to try to investigate these questions? And the first thing we're going to need is MHD. And that's because we now know that the accretion flow itself is driven by magnetic processes, so-called magnetorotational instability. So this is a local linear instability with a very large growth rate that occurs in a Keplerian rotation field in plasma, magnetized plasma orbiting around a compact object, or indeed any plasma in any Keplerian flow. And the instability itself can be discovered analytically, if you like. You can get the dispersion relation, but to study the nonlinear regime of the instability really requires numerical methods. And so this little movie that was playing here was showing you a small little piece of an accretion disk, and it was showing you the evolution of the angular velocity fluctuations generated by the magnetorotational MRI, the magnetorotational instability. You see the linear modes emerge, and then they go fully nonlinear and generate turbulence. And so if we want to understand this turbulence, which indeed sets the mass accretion rate and sets the angular momentum transport rate in the flow, we need to use MHD methods. You have to incorporate magnetic fields directly. You can't just model this with a viscosity. It needs to be modeled with full MHD. And so MHD is essential for modeling black hole accretion flows. And we can either use so-called global simulations, which I'll talk about mostly today, in which we model the entire accretion flow over many decades in radius. Or we've learned a lot about the MRI from so-called local simulations, where you just study a small little patch of an accretion flow using appropriate boundary conditions to focus all your computational effort on a smaller area. So both local and global simulations have taught us about the MRI, and these are going to be required, and MHD is going to be required to model these black hole accretion flows in the luminous state. But in addition, we're going to need to incorporate radiation fields, and that's straightforward from the so-called Eddington limit I've already mentioned a few times. So basically, spherical accretion is clearly only possible when the outward force from the radiation field exceeds or is smaller than the inward pull of gravity. If the radiation exceeds gravity, you'll just blow away all the plasma. The radiation force will exceed gravity, and you'll produce a wind and not an accretion flow. So these two forces balance when the radiation forces, which is just the intensity, specific intensity, luminosity over the area at some radius r, times the electron scattering opacity, is equal to just the, far away from the black hole. You can just use the Newtonian gravitational force on the protons, but the electrons and protons are tightly coupled by electrostatic forces. So while the photons interact with the electrons, the mass is all in the protons. And so you put this in the proton mass to compute the gravitational force, and the electron scattering opacity to compute the radiation force. So a very simple formula, which gives you the so-called Eddington luminosity. If L is bigger than this Eddington luminosity, you should not be able to get spherically symmetric accretion, because the radiation pressure on the electrons and indeed the plasma would exceed the inward pull of gravity, and you should get a wind. And indeed, whenever the luminosity is close to Eddington, in fact, even just 10 to the minus 2 Eddington, then you're going to need to incorporate these radiation forces, because they're very, very important in producing the accretion flow itself. And so we need to include both radiation and magnetic fields into these calculations. So if we're not studying the flow close to the black hole, if we're, say, 10 or 20 or more RG away, we can just write down the Newtonian equations of radiation MHD, which I've done here. So while this talk is about black hole accretion flows, I'm going to write down the Newtonian equations for MHD. The black and blue terms and equations represent the fluid dynamics, mass conservation, momentum conservation, energy conservation, and Maxwell's equations to evolve the magnetic field for a magnetized fluid. And then in addition, we need to add in the radiation forces and the momentum equation, this minus G representing the radiation force, and the net heating cooling rate due to photon material interaction is a source term in the energy equation. And then to compute these terms, they're just moments of the specific intensity of the radiation field. That requires integrating the radiation over all angles and frequencies at all positions in space using the rate of transfer equation, written in red on the bottom. So in principle, we have a straightforward, well-posed, closed system of PDEs, where the source terms in the fluid equation just come from angular quadratures of the specific intensity to calculate the heating, cooling, and radiation forces in the lab frame. And there's no missing physics, no subgrid needed here. And so I always say this in many ways is an easier computational problem than many others in astrophysics. For example, in galaxy formation, where there's small scale processes that are unresolved on the computational mess, feedback from star formation and turbulence and so on, that have to be included through some kind of subgrid prescription. And here there is no subgrid models, no subgrid physics needed. In principle, these equations describe the dynamics of the plasma, and we just need to solve them as accurately as we can and understand the resulting solutions, and that will tell us about black hole accretion flows. And if the solutions don't match the observations, we're going to learn some very interesting physics, because that would say there's something missing here, but what could be missing? There would be some other very interesting physics going on. And so in some ways, these direct ab initio models are possible in these flows. So despite this being a complicated system of equations, I admit that solving these equations is not easy. At least at the end of the day, we're not missing something else. And I think that's something to be said. So solving these equations, as you might guess, analytically in full 3 dimensions and time-dependent flows is just not possible. And so computational methods have emerged as being absolutely crucial. And why are they so useful and important? Partially because of faster computers, mostly because of better software. So I want to just say a couple of words about those, about the computational approaches used here. The faster computers, if you're not aware, or if you've not seen this before, you might find this of interest. This so-called top 500 list is a list of the world's fastest computers. The red line is the #1 computer at any given date at time. The blue line is the sum of all the computers in the top 500 list. And the yellow line is the slowest computer on the list. And the performance is measured in gigaflops. So a teraflop is this line here, petaflop, exaflop, and the list is created in 1993 and has continued to today. And so what's amazing about this result is this exponential growth, Moore's law, which has shown you the growth of the fastest computers. Moore's law has not stopped. The power law may have broken around 2012 or so, but it's still continuing as an exponential growth. That's because the technology changed, and previously it was faster processors. Nowadays, it's more parallel processors, and that the growth rate is slightly different. And you can also see trends of technological advances that make the #1 computer suddenly jump up very quickly. And then the technology doesn't change for a while, and it jumps up again. We're about to jump into the exaflop era this year, as more than 1 exaflop computer is installed around the world in this coming 2022. And so obviously this drives a huge expansion in computation. It's analogous to my observational colleagues having their telescopes, expand in aperture, exponentially in time, which for them would be, absolutely amazing. But that's what's happening in computation. What we can do is exponentially, getting faster. And that's pretty amazing. But in fact, the #1 driver of computation and the importance of computation is not the increase in computers, it's the increase in improvements in software. A better algorithm always beats a faster computer. And so nowadays we have very sophisticated algorithms for doing computational fluid dynamics in curved space-time with radiation transport. There are many such codes available and have been implemented. I've been working with one in particular called Athena++. This is just the one code that we've been working on, but there are, literally dozens of groups around the world developing these application codes and many other codes around. Athena++ implements so-called constrained transport algorithm for MHD, adaptive and static mesh refinement. I'll say a few more words about some of these features. Includes GR and stationary spacetimes, and most importantly, full transport radiation transport for doing these calculations. So the sort of things that are really important for what I'm talking about today are the red highlighted things, this MHD, as I mentioned, and radiation transport, along with adaptive mesh refinement and good scaling and performance, are all what enable the kind of calculations. If you just gave us the world's biggest computer, but without the software to run on it, it's pointless. You have to have the software that can take advantage of that. And the software is really the intellectual effort that's required for these to make progress in this field. So the important ingredient of this is adaptive mesh refinement. For those who are not working in computational fluid dynamics, let me just explain quickly what that is. And basically, your computational domain is broken up into blocks. Here, this domain is broken up into 3 by 3 blocks. It's two-dimensional domain. And if there's some region of space where you would like to resolve it better with smaller cells, finer resolution, then you just divide the blocks into smaller blocks and keep subdividing those smaller blocks into yet smaller blocks. And so you can concentrate very small spatial grid cells in regions in the volume of the domain that you need them, and you don't waste a lot of resolution or fine resolution in areas where you don't need it. And so this adaptively changes the spatial resolution to the flow to resolve small scales where you need it. And this block-based refinement is what we've implemented in Athena++, very similar to what in another code called Flash, but quite different from codes like Pluto and ENSO. For those, again, who are familiar with astrophysical fluid dynamics, you may know some of these codes. This block-based AMR really works well on modern parallel computers because communication is only required through the boundaries. It's very, very efficient on very large parallel systems with large core counts. And indeed, I think this block-based AMR is becoming sort of the de facto standard now for large-scale computing systems. Another feature to get good performance on parallel systems is the ability to interleave calculations and communications. And this can be done through something called dynamical execution, where each processor is assigned many, many blocks. If you go back, I mentioned these mesh blocks in the previous slide here. These, the domain is divided into these blocks. Well, each processor on the computer can be assigned many, many, many of these blocks. And the integration of each of those blocks is independent. And so the blocks are organized into a dynamical execution procedure called a task list. So part of the execution requires communication between processors through something called the message passing interface. And the calculations and communications can be overlapped. You can be communicating on one block while you're computing on another. And that allows you to hide all the communication on the computer behind calculations and allows you to run on very, very large core counts at very, very high efficiency. So again, through the evolution of algorithms and software that has emerged this dynamical execution model. And again, it's important for being able to run in very, very large core counts. And again, this is implemented in Athena++. And then finally, we need to know that our algorithms are accurate, that they're calibrated, that they're really giving you the right solution, that our approximations that we implement in the methods are giving you and converging to the correct solutions for the equations of fluid dynamics. You can do that by comparing to analytic solutions, and you can also doing it by comparing to other numerical solutions for fixed test problems. And a very popular test problem is studying nonlinear regime of instabilities, fluid dynamical instabilities. For example, the Kelvin-Helmholtz instability that occurs when two fluids are shearing past each other through an interface. Then that interface is unstable to the development of rolls and substructure. And this is so-called Kelvin-Helmholtz instability. And what's shown here is the results from a calculation using Athena at different resolutions and a spectral code called deadless. Each row here is the solution at a given time, and each vertical column is the Athena solution at either 4096 squared, 8192 squared, or a deadless at 4096 squared spectral elements. And you can see as you increase the resolution with Athena, pixel by pixel, the solution is identical to the deadless 4096 solution. At Athena 4096 squared, there are some slight subtle differences between the secondary KH rolls that deepen the nonlinear regime. But at 8192 squared, the Athena solution is basically pixel by pixel identical. And you can be much more quantitative. You can calculate the L1 error norm between the two solutions as a function of time. And you can show how the solution converges to the deadless solution. And indeed, at 8192, the error, maximum integrated L1 error is at 10 to the minus 5. So it's single precision on a computer, which would basically converge to the spectral solution. And so with these finite volume methods implemented in modern codes, you can get spectral resolution at half the cost, because even at 8192 squared, Athena runs much, much faster than spectral codes because they're much more expensive, requiring all-to-all communications and FFTs. And so, you're able to calibrate your methods and confirm they really are giving you as good accuracy as sort of the best algorithms we have for fluid dynamics spectral methods, and it gives you confidence that your methods are working. So let me say also about the radiation transport methods, because again, this is crucial for studying radiation-dominated problems. We simply discretize and evolve the frequency integrated radiation transport equation, as I wrote down earlier, typically using roughly 100 angles at each grid point. Then we can take angular moments of that specific intensity to calculate the heating rate and force. Because this greatly increases the complexity, because we have 100 more variables per grid point, 100 angles. We have specific intensity to 100 angles, but the cost to integrate the radiation transport equation at any given angle is much less than the cost to integrate an MHD equations. And therefore, we can roughly afford to do 100 angles at the same computational cost as doing the full MHD. And so this makes the problem tractable. And because we're solving the time-dependent transport equation, it's suitable for relativistic problems. We're following the dynamical evolution on the light crossing time by solving the time-dependent transport equation. Currently, we have a frequency-dependent version is working as well, and we're currently doing new calculations with frequency-dependent transport. And these full transport methods are really quite important, because current generation of modeling radiation transport typically involves approximate methods. For example, flux-limited diffusion, or FLD, which involves simply reducing the transport equation into a two-temperature diffusion problem, or so-called M1 methods, which assume an analytic closure for the moments of the radiation field without actually solving the transport equation directly. And through various test problems, you can find differences between direct solution of the transport equation using so-called variable Eddington tensor methods like VET versus M1 versus FLD. So here's a test problem where you have a hot plate emitting photons into an optically thin medium. The hot plate extends from -1 to 1 in this domain here. And you just simply calculate what the radiation energy density is above this hot plate as photons emerge. And the solution from this variable Eddington tensor M1 and FLD methods are shown in this panel here. The analytic solution, the exact solution, is the black lines, and the red is, again, the VET solution repeated. And so clearly these direct transport methods converge to the correct solution. They are consistent with the underlying PDEs you're solving, whereas M1 and FLD does not converge to the solution of the transport equation for simple test problems like this. And this is a relevant test problem because our accretion disk in the low luminosity cases will be this thin disk, which will be like a hot plate, and we want to know what the radiation field is above the disk. And so, these full transport methods potentially will be important. We need to, it's important in the future to be able to calculate these flows using these full transport methods. while early solutions using other methods are certainly warranted and very important, ultimately we want to study these flows using these full transport methods. And without belaboring, again, we can test that our full transport radiation is working, again, through both analytic and numerical problems. So a great analytic problem is the dispersion relation for linear waves. So these are just basically sound waves in a radiating dominating plasma. You can calculate the phase velocity and damping rate due to the emission, absorption, and radiation for these sound waves. And the analytic solution are the red, blue, and black lines computed for different ratios of the radiation to gas pressure. So it's a parameter in the problem. And then the stars are the numerically measured phase velocity and damping rates from our code using different optical depths per wavelength. That's the x-axis here. And so you can see excellent agreement between the numerically measured dispersion relation for these waves and the analytic solution over a wide range of parameter space, optical depth, and radiation to gas pressure ratio. And again, you can be more quantitative and calculate the L1 error norms for one of these points and show that they converge with numerical resolution in regions which is not radiation pressure dominated. You get second order convergence because we're using a backward Euler implicit scheme. There's first order convergence where radiation pressure dominates. And that's these two curves here. And by the way, this convergence demonstrates the importance of algorithms, because notice that second order algorithms give you, up to 2 orders of magnitude lower error than a first order algorithm does for the same problem. And so you would need a computer, or you would need a resolution 100 times higher per dimension in a first order algorithm to get the same accuracy. In 3D, that's 10 to the 2 to the 4, that's 10 to the 8 times more expensive. So no computer advancement is ever going to beat a second order algorithm compared to a first order algorithm. No improvement in computer speed is ever going to make a first order method be more accurate than a second order method. And so this is a demonstration of why it's so important to have accurate algorithms, and why it's really the improvement in algorithms, not the faster the computers, that's been the most important advancement in being able to do computational problems accurately and robustly. That problem is linear, so we want to study nonlinear evolution of turbulent flows, and so you want a nonlinear test problem, and that can be provided by radiation-dominated shocks. Again, this is just a one-dimensional plane parallel steady-state shock for which there's a semianalytic solution shown in the red dotted line, and again, you can set this solution up with the numerical code, and you get excellent agreement between the two. Again, you can compute L1 errors. Now they converge at first order because there's a discontinuity in the problem, and everything is first order for discontinuities. But nonetheless, you recover all of the structure of the radiation-dominated shock, including this radiative precursor, which heats the temperature upstream of the shock wave, and the so-called Zeldovich spike, which is a post-shock cooling region due to the emission of radiation. And so, again, we can confirm these methods are working well on radiation-dominated problems. Again, I mentioned performance is important, and we get excellent scaling. So up to 1,000 nodes, which is more than 500,000 cores on modern parallel computers. So these are exascale computers. These finite volume methods show performance which does not decrease with number of nodes being used. That is, the performance per core out to 500,000 cores is roughly the same. It's sort of 95% the same as it was if you're just running on one processor. So you have 95% efficiency running on the entire machine out to 500,000 cores. So these finite volume methods show excellent scaling on modern computers, and these large-scale computers, therefore, and these methods are well suited for large-scale parallel computing for these kind of problems. Moreover, many computers nowadays are accelerated by devices like graphical processor units like GPUs. And again, these methods port well to GPUs. So here's an example of the implementation of Athena++ onto a GPU using the so-called cocos performance portability library on a single GPU for large enough, this shows you the performance versus the size of the mesh on the GPU. A 32 cube mesh is just not big enough to keep a GPU busy, and so the performance is low. But on a 256 cube mesh on a single GPU, you're getting over 100 million zone cycles or zone updates per wall clock second on a single GPU. And in comparison to the CPU, it's more than 20 times faster. And so you get excellent performance and improved scaling or improved performance on GPUs. In fact, I spent my pandemic rewriting Athena++ into Cocos, and there's a new version, including full GR and full radiation transport that we've just finished. We're now currently running on parallel systems to do a whole new series of GRMHD calculations with radiation transport on GPU accelerated machines using this Cocos library. And so again, these 5 volume methods scale and adapt extremely well to modern computing systems, including GPUs. So let me talk about some of these results now. And I should first say something about previous work. We're not the only group working on this. And indeed, for the last 5 to 7 years or so, people have been pioneering studies of GRMHD accretion flows, including radiation. I think the first papers were by John McKinney and Oleg Sadowski, more than 6 years ago, where they did similar to that EHT model I mentioned very early on. They've been doing GRMHD calculations as a poloidal slice of the density, and the flow streamlines are shown here. And this is an equatorial slice of the same flow at some late time in the flow, where they've done a accretion from a torus, including radiation calculated using the M1 approximation. So again, these are pioneering calculations using an approximate method in full GR to try to understand the effects of radiation. And one of the important results from these calculations is measuring the radiation efficiency. What fraction of the energy released by accretion is released by radiation versus what fraction goes into the black hole. And they get radiation efficiencies of 10% or so in these calculations, which are very intriguing. And more recently, I think Matthew Liska and Sasha Tchaikovskoy have recently published or presented a paper, posted a paper in which they have repeated these calculations using the same numerical methods, but now on a GPU accelerated cluster, so at higher resolution. And again, are reporting similar results, but with new sort of thermal instabilities emerging, new clumping produced at very high resolution. And so again, these are very interesting and important calculations to understand these accretion flows using these approximate methods. And our goal is to try to repeat some of this using these full transport methods to A, confirm the results, and B, understand the accretion flow at higher luminosities using full transport methods. We've been using time allocated to us from the DOE Insight program, which provides access to very, very large computers like Mira. We have not been doing full GR, but have been using Newtonian calculations in a post-Newtonian potential. That means our calculations are only relevant, say, beyond 10 or 20 RG. We've been using this full time-dependent radiative transfer method, 80 angles per grid cell, a factor of 1,000 in dynamic range and radius, with AMR to give us resolutions in the inner regions of about 1,000 cubed grid cells. And what's shown below is a movie of the density and velocity streamlines resulting from one of our calculations. And you can see how MRI turbulence develops, generates all sorts of fine scale structure. And it also, most importantly, produces an accretion flow inwards. And then the radiation field is generated dynamically and self-consistently by this accretion flow as the plasma is heated by the accretion. And we follow the feedback and cooling and the radiation forces by solving the rate of transfer equation simultaneously with the MHD equations as the flow proceeds, the calculation proceeds. And so to show you what the radiation field is doing in that calculation, this movie shows you the radiation flux on an equatorial slice. Blue is outgoing radiation flux, red is ingoing, and we're going to just move outwards. The sphere will slice the data at larger and larger radii. The radii is shown somewhere right here. This is RG where it's being sliced, 150 RG. you can see that there's mostly outgoing flux in the polar regions, and in the midplane and the equator, where there's MHD turbulence and the radiation is trapped in the plasma, you see the turbulent eddies are generating both inflow and outflow as they drag the radiation field around. Most of the radiation is escaping in the polar regions in this very big, large wedge. So already you see a hint as to how you get around the Eddington limit. You do it by having non-spherical accretion. Accretion is primarily occurring at the midplane at the equator, and the radiation is escaping along with matter. There's a powerful wind generated by the radiation forces. The outflow is primarily occurring in the poles of the flow, while accretion is proceeding at the equator. This calculation generated super Eddington accretion. That is to say, the mass accretion rate compared to the Eddington rate. That is, the Eddington rate, mass accretion rate, is what would produce the Eddington luminosity at 10% efficiency. So we're getting Eddington ratios that are 100 or more in these calculations, depending on what magnetic field geometry we assume, which drives the accretion through the MRI, and depending what the surface density of the disk is initially. So the number at the end is that labels the run is the accretion rate and the Eddington the mass accretion rate of the Eddington rate. So this is 150, 33, 25, and 52. So you see the accretion rate is highly variable, but there's a long-term average value, which can be, in this case, 150 times Eddington. So very highly super Eddington. And, so some of the important results to come. One is that MHD turbulence is very important for transporting radiation in the disk itself. So these two images show you the correlation function between the density and the magnetic energy, B squared. Black is negative, so they're anti-correlated. Red are positive, they're positive correlated. You can see in the equatorial plane, these two quantities are negatively correlated, mostly black, meaning that where the magnetic field is large, the density is low, meaning there are bubbles of high magnetic field strength and low density. And those bubbles of high magnetic field are positively correlated with outgoing velocity, Vz. So again, there's these red positive correlation functions between Vz and B squared, meaning that these low density bubbles where B squared is large are moving outwards in the disk, carrying radiation with them. They're filled with low density, low optical depth regions filled with radiation that are transporting energy out of the disk. So basically, turbulent convection is cooling down the radiation, cooling down the accretion disk. And this actually exceeds the diffusion rate of photons in the disk. It's not rate of diffusion that dominates cooling in these radiation dominated disks, it's turbulence driven by the MRI. In the same way that convection can dominate over rate of diffusion inside stars, in this case it's turbulent convection by the MRI that dominates over rate of diffusion. That was unexpected and is not incorporated in analytic models of radiation dominated disks. And so, but it's a very important contribution to the energy budget of the disk. So that's something that emerges from these calculations. We have radiative efficiencies that get small. This eta rad is again, the efficiency with the fraction of radiation, fraction of the energy released by radiation versus the fraction accreted. And it's only 1% for this 150 times the Eddington ratio calculation. And it's smaller than the values that the McKinney and Sadowski and others get using M1. And that's interesting, that's intriguing. Is that something because of the numerics or something because we're doing something different in our initial conditions? We really need to understand that. But what we find is that the Eddington or the efficiency drops as the Eddington ratio gets larger, resulting in a total luminosity, which is roughly constant. The actual total amount of energy released by the system is roughly 10 times the Eddington, and never gets larger than that because their efficiency drops to compensate the additional accretion energy released at higher accretion rates. What about sub-Eddington disks? We can also use lower surface densities in the torus initially and study mass accretion rates that are therefore smaller and therefore produce sub-Eddington accretion. So we've done calculations where the mass accretion rate is only 0.07 times the Eddington mass accretion rate. So m dot over Eddington saturates highly variable, but saturates at roughly 0.07. And we can actually calculate the luminosity as a function of time from the system. These are light curves. So these are, calculated ab initio light curves from accreting compact objects. What's interesting is that often the m dot is used as a proxy for the luminosity. If you don't incorporate radiation transport, you only have the plasma. Often people use m dot to estimate what the associated luminosity of the accretion flow would be. And you can see there's not a very good correspondence between m dot and the actual emergent intensity that comes when you do a full radiation hydro calculation. Therefore, m dot really is not a very good proxy for the emission released in this accretion flow. We've also done models which are 0.2 Eddington. So we've spanned, about a factor of 10 in Eddington ratio below 1. Again, we have mass accretion rates and light curves for those systems. And they're very interestingly different. So this is kind of a Ruge's gallery, snapshots of the time averaged and azimuthally averaged structure of the accretion flow from super Eddington, 150 times mass Eddington mass accretion rate here, all the way down to the lowest model, 0.07, and spanning the full range, 33.2 all the way down to 0.07. So you can see as the Eddington ratio gets smaller, the disk gets thinner and thinner. It cools down and gets thinner. So the colors are the density. The streamlines here are the velocity streamlines with the color measured in fraction of speed of light. You can see that the sub-Eddington ratio models produce very, very thin disks. The black dotted line is the photosphere, the optical depth 1 surface, and the photosphere gets very, very thin close to the disk surface. You also see an outflow, a strong outflow generated in these sub-Eddington disks. And so the structure of the disk qualitatively changes as you go from super Eddington down to these sub-Eddington disks. These sub-Eddington disks is what we would think a normal AGN Seyfert galaxy would look like. This is the kind of parameter regime such disks would be in. These disks are thermally stable. Let me not say much more about that. There's interesting predictions. These radiation dominated disks should be thermally stable. It turns out that magnetic pressure probably stabilizes them. Instead, let me say something about radiation stress, because another resulting surprising result that came from these calculations is that these low luminosity, so sub-Eddington results, 0.07, the Eddington ratio results, show that radiation stress is really important in the upper layer. So what's plotted here is, again, the time and azimuthally averaged toroidal stress on the plasma. The Reynolds stress, that's the fluid stress due to non-axisymmetric velocity fluctuations in the flow, that's Reynolds stress. There's the Maxwell stress due to magnetic torques on the flow, that's produced by the MRI. And then finally, there's the radiation stress, because the radiation field can produce, just like particle collisions can transport angular momentum, then so can photon collisions with electrons transport momentum, and they can transport angular momentum. And so there's a non-axis or a non-diagonal component to the radiation stress tensor, which is equivalent to radiation viscosity. And that's what's plotted here, the R phi component of the radiation viscous stress tensor. You can see that in the midplane of the disk, the MRI dominates. So it's magnetic torques that are driving the inflow in the optically thick midplane of the disk, just as we have understood for many decades that magnetic fields drive the accretion. But in the optically thin upper regions, it's viscous torques that are dominant, and they actually drive a surface accretion layer. Again, that was kind of unexpected. And another difference with more approximate methods like M1 is that M1 cannot capture the non-diagonal components of the stress tensor. They're assumed to be 0 in M1, and so it's important to use these full transport methods again to assess the importance of the radiation stress on angular momentum transport as well. And then finally, there's very interesting results about the thermodynamics of the plasma and these sub-Eddington disks. So in particular, for the 0.07 mass accretion rate, this is again a plot of the temperature in the time and azimuthally average flow. The temperature you can see is extremely high above the surface layers of the disk. Again, that's the formation of extremely hot plasma in the corona of the disk, basically. And the reason why is because this plasma is optically thin. It's heated by magnetic dissipation of turbulence, but it cannot cool because it's optically thin. And so it just heats up to very, very high temperatures. And so we see spontaneous emergence of extremely hot corona at low Eddington ratios from these radiation MHD calculations. Again, in agreement with observations of, say, Seyfert galaxies. They don't appear in the super Eddington flows because the photosphere is confined to the polar regions and most of the flow is optically thick. But at the low luminosity where the photosphere is much, much closer to the equator, that's where we see the emergence of these corona. We've tried spectral fitting of some of our results. So we've taken a snapshot of our calculation and we fed it into a Monte Carlo radiation transport code, which does full frequency and line dependent transport. And then we used XSpec to compute the opacities for that calculation. And we've computed synthetic spectra. And this black wiggly line is the spectrum from one of sorry, that's the blue and green curves are spectra computed from different regions of our calculation, resulting in the red curve, which is the sum of the spectrum of over the entire radial range of our calculation. And the black curve is an actual observed spectrum for an ultraluminous X-ray source observed by NuSTAR and XMM Newton with his phone number here, NGC 1313X1. There's surprisingly few free parameters in this calculation. Basically, there's only one, the mass accretion rate. We don't know from the observation what the mass accretion rate is, and that moves this curve up and down vertically. That sets the normalization. So we've chosen a mass accretion rate that fits the curve, and we get an excellent agreement. And the mass accretion rate that we choose is actually quite reasonable, ends up being tens of the Eddington rate. And we know this is a superluminous source, and that agrees very, very well with what we might expect. And so these spectra are very promising in that we can reproduce the broadband spectrum of at least the ULX sources from these calculations. So let me wrap it up. I know I'm running out of time here by returning to those observational questions. How does super Eddington accretion occur? Well, we think it occurs from these non-spherical geometries, with cooling from turbulent transport being an important part of the agreement, or an important ingredient of the flow. It's important for cooling the disk and allowing photons to escape the system. How do accretion disks form corona? Well, we see in these sub-Eddington disks that above the photosphere, the plasma is unable to cool, and that you can generate very, very hot plasma. In detail, we are not able to reproduce the spectra yet. It needs a better model for Compton cooling in the coronal regions, which dominates what sets the temperature. It's the dominant physical process setting the temperature in the corona. And so we have yet to, we have more work to do in order to actually reproduce the spectrum observed in these corona, but it's at least a promising step in the energetics. And then finally, we have some promising spectra, and we're certainly working very hard to do full frequency dependent transport to compute ab initio spectra and test this continuum fitting model that I mentioned at the very beginning. So let me just summarize by saying, with modern computational methods, we're able to do full radiation MHD calculations of these black hole accretion flows. Other groups are doing these same kind of calculations in full GR with approximate methods. And in the future, we plan to also be doing full GR to study these super Eddington and sub Eddington accretion flows. And I've got some bullets summarizing some of the points I've made already. And I'll just quit here and answer any questions if there are any.
Thank you. Thank you very much for this great talk. There are a few questions. Let me start with one that we have on our YouTube channel. I'm going to paste it here. I think I can, in case you also want to read it yourself. Okay. So it says, I'm interested in the study of the magnetic field and the behavior of turbulence in the accretion flow in Sagittarius A star. Do you know some important numerical results to consider in this? Thank you. And this is from our YouTube channel.
Yes. So I mentioned this magnetorotational instability, first discovered more than 30 years ago in 1991. And in the intervening 3 decades, there has been an awful lot of work in trying to understand magnetic fields and MHD turbulence and accretion flows. There are a couple of excellent review papers by Balbus and Hawley that you can look up. There's a paper from 2001 and one from 1999. So if you just search on the archive for Balbus and Hawley, there's a review of modern physics paper, which already now is almost 20 years old and somewhat dated, but provides an excellent overview of many of the numerical results on the MRI. There's, to be honest, probably by now hundreds to thousands of papers written on numerical modeling of the MRI. I certainly couldn't list them all. That's why I would suggest starting with one of those review papers and then looking in from there. I hope that helps.
Okay, thank you. We can see if there's a follow-up from that. I have another question here, and it says, like, could you please comment a little bit more on the GPU implementation and which part of the computations are more susceptible to be written for GPUs?
Sure, this is the latest stuff we've been doing. So I've been reluctant to adopt GPU computing for a very long time, mostly because it required special hardware-dependent libraries like CUDA, which meant that if you write your code in CUDA, you can't run it on your laptop anymore, and you can't run it on CPUs anymore. And I simply didn't have the resources to support multiple versions of a code to run on multiple different platforms. But what's changed in the last 5 years is the emergence of a number of open source libraries that allow you to write code that runs on any architecture. There's been a long interest in this using things like OpenMP and OpenCL. However, the challenge of those libraries is they require the vendor to implement compilers that implement those standards. OpenCL and OpenMP are just a set of standards that requires the vendor to build a compiler that meets those standards. And to be perfectly honest, the vendors don't have a whole lot of motivation to write those compilers. So instead, this cocos library has emerged. It's spelled Kokkos. It's simply a C++ library. It's basically a translator. It turns whatever code you write in cocos into either standard C++ that can be compiled by any compiler, GCC or Clang, into executable for a CPU, or it will turn it into CUDA if you're running on an NVIDIA compiler, or it will turn it into SYCL if you want to run on an Intel GPU. And so it takes away all of the work for you. You write one code in one language and it provides performance portability. So that's what we've done. We've rewritten Athena in cocos. It's just C++. I mean, you can't tell the difference. It's just C++. And it works exceptionally well. We've been able to run on any kind of GPU. And some of the key aspects are you have to move the entire calculation in the GPU. So all of the data, all of the calculation sits on the GPU. We only move data to the CPU to do outputs or to do control logic. All the Riemann solvers, reconstruction, everything is on the GPU. All the AMR logic is all on the GPU. It runs on multiple nodes using MPI. There's CUDA-aware MPI that allows you to do GPU to GPU MPI communication. So I've been very happy with how cocos works. You know, what the future is, I don't know. You know, 5 years from now, will cocos still be around? I don't know. I think what's going to happen is C++ is going to embed some of the functionality that's in things like cocos. You know, it's inevitable. You know, computing has become heterogeneous. There needs to be a way to program architectures that have different memory spaces, devices and hosts, different execution spaces, and that needs to be embedded into the languages that we're using. And so a future version of C++ is going to have to embed this in, and therefore I don't care. I'll just use that when it emerges. And I think cocos if you write your code in cocos, it will translate into whatever the syntax that C++ provides in the future seamlessly. And so I have now become a GPU believer because you can now write portable code that can run on anything. I develop it all on my laptop, and then I run it on GPUs in the office, as when I'm ready to go for into production mode, and it works seamlessly.
Great.
A long answer, because I've been spending a lot of time working on this and so.
No, awesome. I think that's what we want, actually. Thank you. So I think there are a couple of questions also on YouTube. Let me see before I read those ones. Is someone here, the coordinators, have questions?
Yes, I have a very
Yes.
naive question. In the sense, because of, as far as I understood, is the spectra that you observe with X mass or new star is the kind of the time independent spectra. So my question is, what would happen in the case if the accretion flow changes in time? Is time independent? Like you have a transient? Is it possible to, or it's gonna take it much longer to?
Right.
Because of the resolution, the time.
Right. Very good question. So you're absolutely right that we're computing the time evolution of the flow, and so in reality, the spectrum is evolving in time. And in fact, it's well known that AGN are highly variable. You look at them from night to night and they change, from month to month they change. In fact, they're so-called changing look quasars, where over the course of a few, changing look AGN, where over the course of a few years, it'll change completely from a Seifert 1 to a Seifert 2. And so the problem is that variation in timescales. The variability that we capture in our calculations is the variability associated with the flow at a few hundred RG, which is very, very short. That's hours to days to months. And the year variation is occurring at much, much larger radii, which is very hard to capture in these kind of numerical simulations because it requires a very, very big box to follow the disk out to thousands or tens of thousands of RG. And so to be honest, modeling the variability on long timescales through direct simulation like this is going to be very, very challenging. Instead, the kind of data sets that we can compare to are AGN variability or black hole variability from these X-ray binaries. Again, for a stellar mass black hole and X-ray binary, there the variability is on millisecond time scales, because that's the basically orbital time for a stellar mass black hole. And indeed, we have all these X-ray satellites for the last few decades that have been timing missions to study the variability of X-ray for emission from black holes and stellar sources. So we have this amazing data set that we can compare to on orbital timescales at the event horizon. And that's really what we should be doing. And another related point for you, this question is very, very important because it brings up many important things. Another important point is that the spectrum we see is the total spectrum of the whole disk. It's an unresolved point source to our telescopes. And so we see emission not just from the black hole and the inner regions, we see emission from far out. We see intervening plasma, we see absorption from gas along the way in the galaxy. And so how you'll correct for that? I mean, our simulations don't include the whole galaxy. So we also have to be very careful about how we actually compare the data. What aspects of the observation are the black hole itself? What aspects are the intervening galaxy? And how do we separate the two? That's going to be very challenging in many circumstances, but very important too.
Okay, thank you.
Thank you. Okay, we have also from our YouTube channel, another question says, the person says, hi, thank you for the talk.
Thank you.
Advection dominates vertical transport only in super Eddington accretion?
So far, from the models we've computed, it's being dominant in a super Eddington case, where the disk is very thick geometrically and it's very, very thick optically. So the photons are trapped and the diffusion time is very, very long. For these much, much thinner disks, to be perfectly honest, our spatial resolution is lower and we have much less dynamic range in the turbulence. And that may be partially an issue. Maybe we're not really fully resolving all of the turbulent cascade in the midplane of these geometrically thin disks. But even so, it seems like the turbulent transport of energy is sort of just less important for geometrical reasons in these thinner disks than in these very thick, sort of wedge-like super Eddington disks.
Thank you. We have another question here from the YouTube. It says, sorry if you mentioned this. Could you comment on the super Eddington accretion and the formation of supermassive black holes? And what is your opinion on primordial black holes at seat of supermassive black holes?
Yeah, these are excellent questions. I mean, that's a very good point that I failed to mention. Yet another motivation of these calculations is understanding the growth of black holes in cosmic time. There's this very challenging issue that we've discovered very massive black holes at very high redshifts, where there really isn't a whole lot of time to grow a black hole, and you really need super Eddington accretion if you're going to do it. You have to accrete for a significant amount of cosmological time at super Eddington rates to get that massive. And these calculations point out that super Eddington accretion is possible. You can certainly do that, and so that's one feasible way. Is it the way that black holes grow at early times? I'm not sure. I mean, that's related to a cosmological, black hole formation question. What is the primordial seeds of these supermassive black holes? Is it direct collapse? Is it merger? That's a very challenging question that I don't know we have the definitive answer to right now. But certainly these calculations are relevant to the growth of black holes in that regime. I think that the answer has to come from the cosmological context. What do I mean by that? Because a real challenge is how you get the plasma all the way down to the black hole at a super Eddington rate over the whole dynamic range of radii. The calculations we're studying, again, are still the inner regions. Somehow you got to get that plasma from parsecs or kiloparsecs away and get it all the way down to the event horizon. And their feedback from the accretion itself, the winds and the radiation field from a super Eddington accretion flow, if it interacts with that gas as it's falling in, it can halt accretion at large radii, where it's only very weakly bound to the black hole. And this is the process of AGN feedback, and that's very important to understand in order to know whether or not super Eddington accretion really is viable for long periods of time. In other words, you need to start with a gas reservoir that's, or you need to supply gas over the whole range of radii for it to really be feasible. And to demonstrate that, it's going to require a calculation that goes beyond what we're doing here, that incorporates the feedback at large radii. It's a very important calculation to do, I think.
Wonderful. Thank you. Thank you, Jim, for your time. For everyone, I think we are already past the hour. Thanks for joining us. Remember, to all the people, we will have more talks. This is our first talk of the year. We have a lot of talks, so you can just go to the whole calendar in our webpage. Thank you very much, and stay tuned.
Thank you.
Go on now. Okay, I think we are not